Good morning. I hope I'm audible. Good morning, everyone. I'm Dr. Saurabh Jogadekar. I'm Assistant Professor in Department of Chemical Engineering at IIT University. I would like to welcome you all for this truly insightful session. Before we start the session, I would request our distinguished speaker, Dr. Polshettiwar sir, Dr. Vaidya sir, and Khati sir to please come on the dais. Today, we dwell into a subject that not only is fascinating but also immensely relevant to the future of our planet, that is sustainable energy and environment. As we embark on this journey of learning, here is an interesting fact to ponder upon. To meet the global climate goals set by the Paris Agreement and limit global warming to 1.5 degrees Celsius, we need to reduce carbon dioxide emission by approximately 45% by 2030 and achieve net zero emissions by 2050. However, even with drastic reduction in emission, it is estimated that we will need to remove around 10 gigatons of carbon dioxide from atmosphere every year by mid of the century. This is where carbon sequestration, both natural and technological, becomes crucial in helping us achieve these targets and stabilize the climate. Innovations in nanotechnology could help us find better ways to monitor, protect, and even restore our ecosystems, playing a crucial role in mitigating climate change. We are privileged to have with us a distinguished speaker, someone whose work is at cutting edge of both nanotechnology and environmental science. He is going to share his views on nanotechnology for sustainable energy and environment. To officially start the session, I would like to invite our Honorable Vice Chancellor, Sir, Dr. Atul Vaidya, sir, to extend a warm welcome to our esteemed speaker, Professor Dr. Vivek Polshettiwar. I would request Dr. Vaidya sir to say a few words before we start the session.
It will not take much time, obviously. Very good morning and welcome to all. Specifically, welcome to Professor Polshettiwar. I know his work in nanosciences, material sciences, environment. And since I worked in dairy for a long time, so I know the importance of environment, chemistry, chemical engineering, and how everything is to be put together to achieve the goals of carbon reduction, or you can say carbon reduction is just part of sustainability. Sustainability is much bigger goal which everybody is trying to get at. Dr. Polshettiwar, his biodata will be read formally. He's a math par excellence, scientist par excellence, professor par excellence, whatever you call it. He has worked extensively in nanosciences, material sciences, basically background with chemistry. And all of us should be proud that he is from Hyderabad. So that is one more thing which encourages us to invite him for lecture here because we are all here, and this institute is also a kind of prestige for the person's farm. And Dr. Polshettiwar is working in EIFR. Institute itself is known for many good scientists, including Jan and Arabican. So you know many good scientists from India, or reputed scientists across the world. They are from PFR, and he's serving there since long. That itself is more than something which is we call a credential. So I will not take much time. I welcome you again. We are all eager to listen, and then I would like our students and faculty to take some hints, and if required, we can take his help in future for collaborative research also. So I think he will be more than glad to help us help us out on this. Thank you very much. You are all welcome. Thank you.
Thank you, sir. Now it is my great pleasure to introduce our speaker for today's session, Dr. Vivek Polshettiwar. Dr. Polshettiwar is a renowned expert in the field of nanotechnology with significant contributions to sustainable energy and environmental applications. His pioneering research has opened new avenues in developing green technologies and innovations that could potentially transform the way we address environmental challenges. To give you a more detailed introduction of Dr. Polshettiwar, I would like to invite Dr. Siddharth Mishra, who will be sharing some background on our distinguished student. So,
Thank you, Dr. Saurabh. It is indeed a pleasure and privilege to introduce our today's speaker, Professor Vivek Polshettiwar, one of the most eminent yet equally sensible and humble personality in the domain of applied chemistry and environmental science. Professor Vivek Polshettiwar presently working as a professor in Department of Chemical Sciences, Tata Institute of Fundamental Research, Mumbai. Professor Vivek Polshettiwar research interests are within the sphere of advanced nanomaterials and nanocatalysts for harvesting solar energy and the transformation of carbon dioxide into value-added chemicals and fuels. The work of his group in the nanocatalysis realms of black hole and defect chemistry represents a quintessential example of how fundamental science can drive innovation in applied research. His pioneering work in plasmonic photocatalysis and defect engineering offers a new perspectives on material design, catalysis, and sustainability, paving the new way for future research that continues to explore the vast potential of nanomaterials in solving some of the leading or most pressing environmental and energy issues. He has published nearly 150 research articles and also filed 12 national and international patent applications. It is noteworthy that one of his publications, Magnetically Recoverable Nanocatalyst, has received almost about 2,000 citations, which is quite remarkable. He is the recipient of prestigious Rice Research Fellowship at US EPA. He has also received an Asian Rising Star Lectureship at 15th Asian Chemical Congress, Singapore at 2013 from Nobel laureate Professor Aiichi Negishi, which is, I hope there is time to clap. Okay? In 2015, he was admitted as a fellow of Royal Society of Chemistry, United Kingdom. He was awarded a bronze medal by the Chemical Research Society of India. He was also awarded the prestigious Material Research Society of India MRSI medal at 2019. In 2021, he was elected as a fellow National Academy of Sciences, India, and further he received in 2022 IUPAC Chairman 7th Prize for Green Chemistry from IUPAC. In 2023, he has received the Falling Walls Award in Physical Sciences amongst top 10. Later in 2024, he was elected as a Fellow, Indian Academy of Sciences, and in 2024 only, he was awarded Shanti Swarup Bhatnagar Award from President of India. It is the highest and most prestigious award given in the area of sciences in India. Sir, we are deeply honored to have you here today. May I now request Professor Polshettiwar to motivate our students and faculty with a glimpse of your research work. Sir.
Good morning, everyone. First of all, I'd like to thank Dr. Atul Vedya for inviting me and giving the opportunity to share the work that we do in PIFR Mumbai. And as introduced, what we are doing in Mumbai is trying to combat the climate change. And we all know the climate change is due to the excessive carbon dioxide, one of the main source of global warming. There are other gases also. We're trying to find out a way to not only capture the CO2, but also so okay. So idea is to not only capture the CO2, which looks like a very easy way to tackle the problem. It is not, but can I use that CO2, capture CO2 to convert into different products and use them every day? That will create some sort of a circular carbon economy. Since the audience is from different areas, the level of the talk I kept is a little bit of a less technical, so that I can convey the message. And hopefully, during the question answers, you can ask me more deep technical questions. What I'm going to do today is I'm also going to explain to you the science behind the climate change. We all listen, read in the newspaper about the global warming and climate change, but several times I feel that the chemistry behind the climate change is not known. For many of us, obviously, experts will know, but especially the students. So I'm going to attempt quickly to explain to you why there is a climate change, how does the CO2 causes the climate change or global warming. Then I will also try to quickly, briefly try to discuss the impacts of the climate change. We always think climate change is all about global warming. There are several other impacts that is really important and we should worry about. And once that is done, then I will try to explain to you what would be the possible solution to combat the climate change, at least technologically. Right. So title of my talk is the nanotechnology, and I also try to introduce some concept of nanotechnology, which I guess most of you know, but still I will try to put in my perspective about the nanotechnology. So nanotechnology for sustainable energy and the environment. And I believe that energy and environment are all connected. We will try to separate it for our simple understanding. So I come from Danish of Natural Research. Before we start, I just want to introduce my institute. This is established in 1945 by none other than Dr. Homi Bhabha, one of the greatest scientists of our country. And this was before independence, so J.R.D. Tata helped him to form the institute, and that's why we have the name Tata Institute of Fundamental Research. But in 1947, this became a government institute. It's no more a Tata company. It's a central government research institute run by Department of Atomic Energy directly. And nowadays we also talk about self-reliant India, Atmanirbhar Bharat. I think this is the important thing for our country, right? We should have been achieved this long back. Now we are still not. But this is one of the best examples of Atmanirbhar Bharat, nuclear energy and atomic bomb, which Homi Bhabha had a vision several years ago, right? More than 75 years ago. And you can imagine our country without atomic bomb, without a nuclear bomb, nuclear energy, right? So you should see this as an excellent example of a vision of one single scientist who was opposed by many around him at that time. Now we are celebrating the fruits of Homi Bhabha's vision. Okay, with that now let us come back to the topic about the climate change. And I personally believe that climate change is the most serious problem mankind has ever faced. Right? This is a big sentence, and that is true. We in Nagpur, I think 45, 46, it's normal, right? We have accepted that it is a norm, but we all know it is not normal. Right? How can it be? We also know that suddenly some cities get flooded, some farming lands become desert. So now it's at our doorstep. Climate change is at our doorstep, and if we don't do anything, those issues, these things will be serious. You may hit 50 or even more than 50, and I don't think we human can evolve so dramatically that we can also live in 50 degrees Celsius. Right? We can't. And we all know that one of the key greenhouse gases is CO2, which there are several other gases, methane and other, but that both can be tackled. CO2 is a problem, and the concentration of CO2 is increasing. Right? Every year it's increasing, and it will keep increasing. That's the way we live our lifestyle. And you can see that the CO2 concentration was nearly the same for many decades, like maybe years. But suddenly at 1750, when there was the industrial revolution, the CO2 emission increased. And this is where we started using more artificial things. So I also try to connect this with our humans, way of living. Right? Also is the real cause of the climate change. So the solution will not only be the science and technology, but also the lifestyle. You can see a dramatic increase when we started using all artificial. You look around us, most of the things are man-made, and every process that makes these things emits CO2. If you make a 1 kg of a cement, it emits around 2.5 kg of CO2. 1 kg of a steel emits around 3 kg of CO2. Every process you see around emits CO2. And we did more cement, more steel, more diesel, more petrol. So we're going to emit more and more CO2. Now, I also try to, I was attempting to explain to you why CO2 causes the global issue with the. Is this okay? Hello, hello. I thought this was good to know. Okay. This is better? Really, oh, that was not working at all. Okay. Okay, but I hope whatever I said until now, you guys followed it. So I will try to explain to you in brief why CO2 causes global warming. I'm sure many of you already know. But I think this can be explained by this particular cartoon or figure, which is known as Earth energy budget. If we ask ourselves what is our energy source, we all say food, right? Roti, dal, chawal. But ideally, if you think deeper, it's the solar energy. Only thing is that we human cannot take the solar energy directly, so trees and plants help us. They take the solar energy, they take water, they take the CO2. So CO2 is ideally our food source. Convert it to different food products that we eat. And that's our energy source. So ideally it's solar energy. So everything on planet Earth is a solar. But how the nature designed the life on planet Earth is solar light will come to the planet Earth. Several portion of some significant portion of it get absorbed by Earth, by this one. You can see some. While I continue with this.
Yes.
Okay. So solar energy comes to the planet Earth, and the cycle is that some energy, a significant amount of energy, get absorbed by different processes on planet Earth, and some energy has to reflect back to the space, right? So that's the cycle, and that's where we can have a nice typical temperature that is required on planet Earth. We have a light, right? Now, what is happening when these outgoing energy, most of the time it's in infrared radiation, or you can call it as thermal radiation. They're supposed to go out into the space. Only some portion should get trapped by the CO2, and that's how we maintain the temperature. But since the concentration of the CO2 in the environment has increased, and CO2 has the ability to trap these outgoing radiation, these infrared radiation, these thermal radiations. So they trap and send it back to us. So what will happen now? More CO2, more trapping, and more energy coming to the planet Earth, and that's how more the CO2, more will be the global warming. And what are the impacts of the global warming? This is one of the cartoons. You can see the annual Arctic sea ice. And look at it here, millions of kilometers. It was 7 millions of kilometers in 1980. And this is data of 2015. So it has reached to around 3.5. 50% of the ice is melted. Right? What will happen now? Don't think that we are in mountain and we don't have a sea. So what will happen? But we all know that we are all connected. Right? We cannot live in isolation. So now, because ice melted, what will happen? The sea level will rise. Right? You can see a dramatic increase in the sea level. And because of the global warming, because the globe is warming, and we know if you heat the water, it will also increase in its volume. So sea level will again increase. Right? And this is something what is happening. We are emitting CO2 uncontrolled way. We are warming the globe, we are warming the sea, we are melting the ice. So everything is in a really wrong direction. And we are doing this even more faster and faster. It's not we are slowing it down. We, in the sense, human or planet, is not India alone, right? Everybody is trying to do that. So if we continue this, there is this very recent paper, a model. He said that all the countries, all the cities near the sea will be underwater. So don't think this is a cartoon. Okay. You guys are ready for it? Okay, this is better. This is better now. Right? Please continue with this. Are you guys able to hear me at the back? Yes. Good. So this looks like just a cartoon, right? So guys, please take this as a very serious thing. This can happen at any time. We don't know the timeline. Right? That is something that I will not able to predict. This will happen to most of the cities near the sea, and that will change the balance. Right? If Mumbai goes into the water, but not all the cities. So this is really serious. The problem with the people, the general people, and also with the scientists, they are not taking it that seriously. They are not really making the attempts to really resolve this. So in addition to the environment and heating and global warming, there's also this. A NASA scientist in 2017 found that when the ice is melting, they are finding lots of viruses and bacteria which were hidden there for millions of years. They are waking up. They're waking up. And they tested the top 18 antibiotics that we have. And none of them work. Now imagine what will happen if those viruses and bacteria infect us. We already experienced the COVID, and it was a big miss. But what positive thing about the COVID is some of the viruses of the COVID family were already there. They were already infected us, so the scientists, chemists, everyone know little about their structure, how they work, how they act. And that allowed us to come up with a vaccine in a year or two. But now think about a vaccine, virus or a bacteria, which is 4 million years of old. Humankind has no knowledge about it. And they infect us. It will be a huge issue, right? It will be a huge challenge. So now, is it too late to stop the climate change? Have we do something, or is it too late? There are two ways to answer this. One is philosophical, which is this: life, the most complex form of matter in the universe, is on course by inevitable change. We accept that okay, this is what is going to happen, and we're all going to vanish in coming few decades or something. That's one way of thinking. One way of thinking. Or we can say, unless we human, the chosen ones, at least we consider ourselves as the chosen ones, can agree to live within the limits of a nature. I think the biggest problem is we misuse what nature gave to us, right? Because the oil, gas, coal was cheap, ideally free, so we took it and we misuse it. We use it more than what we need, right? And that is the real reason for the climate change. So, what it means now that we have to change our lifestyle. Several reasons. It is up to us what happens next. We have to, how many people there on the planet is the key, right? If we have an uncontrolled population, where we come from the nature, and nature has own limits. Scientifically, we need to find a way, energy sources which doesn't emit CO2. We have to stop using carbon-based fuels. No coal, no gas, no petrol. And we all know that is impossible. And we stop it. And we use our electricity, which comes from coal most of the time. Right? So we need to stop it, but we can't. That's how our lifestyle is. Then, if we can't, then we need to also need to understand how much energy we can use. Can I really save the energy? If there are 20 lights here, can I run the same show with the 10 lights? You automatically save 50% of it. And everyone has to do that, not just one place. And this has to be done. Otherwise, you will know. So today I'm going to talk about, are there ways, technological ways to combat the climate change? What we as a scientist, we as a chemist, or chemical engineer can do to stop the climate change. And I guess you all know that India wants to achieve net zero by 2070. For those who don't know what you mean by net zero, so we are emitting around 2.7 billion tons of CO2. We need to find a way either we reduce or we somehow find other technologies to capture those CO2. So that amount of CO2 emitted minus amount of CO2 taken care of equals to zero. Right? That's when net zero. Very simple concept. Unfortunately, coal, gas, and oil still accounts for 85% of our energy mix. Rest comes from solar, wind, around 42% nuclear. And nuclear is the only thing that is ours. We all know that the gas and coal being some. The gas and petrol, everything comes from nuclear. Even the solar cells comes from China. Batteries come from China. We don't have a lithium. That is, the solar is connected to the batteries. So we are not self-reliant in terms of energy. And that's the key for any country to achieve. Right? So now if you look at and look at this, if you look at the slope of this plot, we want to be a developed country. So that means we need to have more roads, more bridges, indirectly more chemicals, more fuels, more steel, more cement. And every more has huge amount of CO2. Right? There is a non-linear relationship between this CO2 emission. So this number is going to be like this, a sharp increase. And where we are now, it looks impossible task. But scientists think about it, there is a possibility. There's always a possibility. And that's what I'm trying to attempt here today. So one simple possibility is I stop using our carbon-based fuels and use solar cells, wind, nuclear. But their contribution, unfortunately, is very limited, especially for our country. We don't still have a sustainable the solar panel technology which can compete with others. We don't have a battery material until we come up with a sodium battery, the other batteries. We don't have a lithium, so we still struggle with it. Even our nuclear energy has remained around 4 to 5% contribution for more than 70 years, and they are also not increasing that. So what it really means is we need to keep using coal, we need to keep using gas, we need to keep using all these carbon-based fuels. That means we are going to keep emitting this fuel, right? So it's challenging now. What do I do? I cannot stop living. So now the simple solution to this is I capture all the CO2 from I found it, develop a technology which will allow me to capture the CO2 from the environment and problem is solved. Right? If you take out all the CO2, 3.2 gigatons of CO2 from India's environment, or 40 gigatons across the planet, the problem is solved. Right? You all agree with that? Once you capture, take it out from the environment, it's solved. Ideally not. What will you do with that amount of CO2? 40 gigatons is a huge number. Maybe you do not know what is the gigaton is. Huge, unbelievable number. So what do you do with the captured CO2? One idea is I drill a hole below the seabed and put the CO2 there. There are lots of dry oil wells. You put the CO2 there. But we all know CO2 is highly unreactive molecule. It doesn't bind with anything. It's very stable. So it will stay there. Some sort of physics of it's like a high pressure gas cylinder kept below us. There will be an earthquake. Everything will come out in one go. And this is reality, a scientific reality. So capture and storage is not really a problem, and not a big solution, not a final solution. It could be a solution to delay the impact of the climate change until we find a real solution. So what could be the real solution? The real solution could be the way the trees does. What trees does? They take the sunlight, they take the CO2, they take the water, and give us all the good products. So ideally, we plant as many trees as we can, and it should solve the problem. Right? Unfortunately, not. The reason is we don't have enough land now to plant the trees. There are lots of studies where say the amount of land required to take care of 40 gallons of CO2 is unbelievable. It's not possible. Obviously, we should plant as many trees as we can so that it will help. That means now I need to develop a trees which can be planted without the land. Artificial trees. I'm basically using some fancy words to attract your attention. So trees which can be planted without the land, we call it as artificial trees. Are nothing but some sort of a material, a nanomaterial, because everyone knows the material. Sand on the beach is a material, as I do. So something like that. You generate these materials, paint your walls, external walls, and they will behave exactly what the trees are doing. They will be taking water, taking CO2, and giving you different products. And they don't need that, right? So that in a technical word is called a catalyst, a nanocatalytic system, which has ability to harvest solar energy, ability to activate CO2, ability to split water into hydrogen and oxygen, take that hydrogen, add it to CO2, and make different products. Methane, ethanol, ethylene, polyethylene, whatever you can think of. We all know that that's the basic chemistry. So how to combat climate change? So I believe this is one of the reactions. It has a potential to combat climate change. Look at the reactions. Carbon dioxide, we have an excess. Water, we have an excess ideally. We use the seawater. Drinking water is another challenge. CO2 plus water, you get a sunlight, you have a free sunlight, and you produce CO plus hydrogen. And mixture of CO plus hydrogen is known as a syngas. And the word syn comes from synthesis. What it means is, if I have these two gases, I can ideally synthesize any chemical that you can think of artificially. This is what industry is doing. Ethylene, propylene, ethanol, whatever you can think, polyethylene, everything comes from these two gases. Obviously, currently they are coming from the petrol and diesel, and that's why they emit lots of CO2. We are reversing that process, and we are saying, okay, now I use the CO2 and water and do this. That solves the problem. And look at this now, circular carbon economy. I develop some sort of material which has the ability to convert CO2 to fuel using sunlight and water. CO2 converted into fuel, you burn the fuel, get the energy, do the function.
they drive the car. And then the CO2 that is emitted goes back to the catalytic reactor, and then you again do a cycle. See, in this cycle, there is no CO2 emitted, and you are still able to harvest the energy, you are still able to do the function. And this is called circular carbon economy. And this is a bit of fancy slide. If this is really true, one day you will have a car which can run by fuel and water. Once in a lifetime you feel. And you may feel how could that be? But one day this will come. And it should come from our country rather than what happened with the deep sea, right? It should not be like that. It should be our own technology. This is possible, this happens in the lab, and we make our attempts, this is possible. Now one can ask this question. Can one chemical reaction truly combat climate change? And it's like a biased statement from the chemist saying that okay, my one reaction will stop the climate change. Whether this happened in our society before that one chemical discovery or chemical reaction discovery changed the society. It happened. 1909, Haber, a German scientist, came up with this reaction, which is nitrogen plus hydrogen to get ammonia. And all chemists, chemical engineers know nitrogen is very stable. So anyone say I want to convert nitrogen into something, they will say, oh come on, you have to read the books. This is illogical. But he did it, he thought in a very opposite direction, and he found that this is possible. And this discovery was in 1909. He made Bosch, which is a chemical engineer in BASF, which is very important, how the fundamental scientists collaborate with engineers. And discovery, which is in 1909, in 1930, just 4 years, they translated that into a commercial process. And believe me, this is 1909, we are in 2025, more than 10 years. We are still using the same process to make our fertilizer. Ammonia gives you fertilizers. Fertilizer increases the farming yield, and that's how we have the food. So there is a calculation where if this reaction is not there, 50% of us will have to do food. Right? So that's the potential of one simple discovery, which can change the human factor. Now we are going to repeat the same history with the other reaction that I told you. CO2 plus water to get you CO plus hydrogen. That's not my belief. Obviously, there are other beliefs. And now, because of that discovery, as we humans are, because now we have enough food, more than enough food. What happened? After the Haber discovery, the population jumped. Look at the population until here, and suddenly look at the population here. And that causes a problem now, because Haber-Bosch produces huge amount of CO2. 1% of the CO2 comes from Haber-Bosch. 1% is a big number. 1 million. So this is again how the human behaves when we see something which is free of charge. Right? We misuse that. We use the excess. This is the example. Okay. Now, if one reaction can really solve the problem, and scientifically, theoretically, at least is possible, then why there are no technologies today? Why there are no commercial technologies? There are a lot of claim about startup, and many of them closed. But there are no commercial technologies. Reason is in a very basic science here. Reason is the stability of the CO2 molecule. CO2 is a linear molecule, right? So this is a carbon and 2 oxygen. It's a very linear molecule. Carbon is sp hybridides. So we all know that makes CO2 extremely stable. And we know the rule of science that if something is stable, it will never convert into anything. It's already stable. Why will you convert it to any other molecules that we need? So in order to convert CO2 into something, I need to put in lots of energy so that you activate the CO2 and overcome that activation energy barrier, and you convert it. But it's like this: you have 100 rupees for CO2 and I'm putting a 900 rupees for energy. Who will do that? No one. And that's the real problem in science now. Amount of energy required to convert CO2 into value-added product is huge. And that's why the process is not sustainable, although it is possible. So what we do in our lab and many other groups do in lab is we try to activate the CO2. And it's very nice chemistry. It's very simple, but that helps in doing the thing. So how do I activate the CO2? So I told you that CO2 is a linear molecule. And because of the linearity, it's very stable. Obviously, there are other reasons. So now then the simple question is, can I bend the CO2 molecule? Don't keep it linear, bend it. And if you bend it, loses its stability, becomes very reactive, and you then convert it to something. Now the question is, how do I bend the CO2 molecule? It's easy to say. So there are very nice ways in chemistry or chemical engineering. And it's also beauty of nature. CO2 with carbon and oxygen. Carbon is a bit of electropositive as compared to the oxygen. Oxygen is electronegative. Now you create a surface which is electropositive, and you bring that CO2 towards the surface. What will happen? The 2 oxygens will get pulled toward the surface. Carbon will stay there. That is bending. You pull it, you mix your surface pulls it, you bend the CO2 molecule, that reduces the activation energy barrier. Right? So it will not be a flat, it will still need energy, but you significantly reduces the activation energy barrier. This is still an area of research. We are trying to really make it flat so that you do the thing at room temperature. Not possible even today. But that's the idea. Simple bending and then you stretch a molecule by designing your material. However, that is just a one step ahead. Other thing is now you still need the energy. So that means the material which is bending and stretching the CO2 should also have the ability to take these photons coming from the sunlight. Because we don't want to put in any energy, we want to put energy which is coming from the sunlight. So we need to design a material which has the ability to capture and pull, the technical word is activate the CO2, and at the same time harvest the solar energy and give it to that activated CO2. So I need a material which is not only catalytic but also photoactive. And this is exactly what we do in our lab. So how do we do that? How do we really design a material which will do all of these things? And there we use the concept of nanotechnology. Say, let us ask this question. We know the sand lying outside doesn't do anything. It's lying there. So what can a scientist do to force that sand to do this thing that I'm telling? Pulling the CO2, harvesting the solar energy. What do I do? So there are different ways. One of the ways is use of nanotechnology. So I will try to first briefly explain the nanotechnology of this for the students, and then I will come back to the use of nanotechnology for achieving this. So what is nanotechnology? Ideally, nano is a scale. Meter, centimeter, millimeter, micrometer, you come to the nanometer, nothing more. Any material which is in the nanometer scale, smaller nanomaterial, right? But if it is just a scale, then how could it be very different? Right? But the scale is too small. Look at the hair. One hair is around 100 microns. So if I want to make, say, 100 nanometer or something, I need to take this hair and slice this hair 1 lakh times. Imagine the hair slicing for 1 lakh times. So you can imagine the scale is very small. You cannot see by the eye. You are using different techniques to electron-based technique to see that. So because it is so small, the properties of the material dramatically change. Even if it is the same material, the properties are not the same when you see the bulb. One of the example is gold. Many of us uses the gold jewelry. Why? Because it's very shiny yellow color. Now ask the question, why it is shiny yellow color? Because gold is metal. Metal has these conducting electrons. They are conducting on the surface. You don't see it by your eye, but they are there. We call them electron cloud. Like the cloud in the sky, you have electron cloud on the surface. When solar photon comes from sunlight, this electron cloud reflects all the photons except some portion of the beam towards the UV edge. That's why you get the yellow tone. And most of the time, all the photons get reflected. That's why you get a shiny color. However, if you convert the same bulk gold into small nanoparticles, 1 nanometer, 2 nanometer, 10 nanometer, you can make a gold of different colors. Same gold, metallic gold, AUG, oxidation, no change in oxidation, no functionalization, no doping, absolutely nothing. It's still same metal chemical composition, but now it shows different color. That's the beauty of nanotechnology. No other technology allows you to change the properties of the material without changing the material chemical composition. This is the only one. Why it changes? Because the electron cloud, which was reflecting the photon when it was in a bulb, when you have a small nanoparticle, that electron cloud is polarizable. You can say movable. Photon, when we say solar energy, has electric component, right? So it's oscillating electric component, and this electron onto the nanoparticle is also oscillating at certain frequency. So when this frequency matches with the oscillation of this frequency, there is some sort of resonance. We call localized surface plasma resonance. It's a simple term. It's just a this resonance, and that resonance allows you to harvest that energy. That those photons goes into the nanoparticle, right? So if I make different particle, I can harvest different wavelength of the light, 400 nanometer, 500 nanometer, 600 nanometer. But in reality, you really need a material which can harvest every single photon coming from the sunlight. 400, 500, 200 to say 1100, 1200, all near eye. So that means I can have a material which take all the energy comes from the sunlight and I give it to the sea. So that was our question then. How do I design a nanomaterial which can take all the photons coming from the sunlight? And that's where we made something called the black gold. It's a gold which is black in color. Again, it's a metallic gold, no doping, no functionalization, nothing, still black in color. The reason is, rather than only playing with the size of the particle, what we did, the idea was that we bring lots of these gold particles together. Say one gold particle having the electron cloud, another gold particle having the electron cloud, you bring together. So these two electron clouds now couple. You make third one. third guy couple, fourth one. And when they have a coupling together, their behavior is very different than the individual particles. They are not still connected, they are at a distance. There is a physical distance between them. But electron cloud couples. And that allows us to now harvest every single photon coming from the sunlight, starting from small portion of UV, entire visible and even near ion. And that's why the material is black. Otherwise, you can also have carbon which is black. But the carbon is black by other reasons. Here are clearly harvesting all the photons. And that's why it is black. Other example of nanotechnology is melting point. Gold melts at 1040 Celsius. But now you can make a nanoparticles which can also melt at 25 degrees. Just make some 1 nanometer gold, rubbing your hand, it melts. Again, I don't really want to go into the deep, but the melting is about moving the atoms away from each other. Right? Now when you have smaller particles, you have more surface atoms. More surface atoms means they are bonded to less number of atoms in between. So when their bonding numbers are less, you will need less energy to pull them away. And that allows you to then melt, melting in just separately, away from each other at a lower temperature. This is a big explanation why they melt. There are various ways of nanofabrication method. One is top down, you take your jelly, break it down to nanoparticles. Obviously it's complicated, right? But there are laser beams which allows you to break it down without proper control. Other method which is simpler and more controlled is I take my atoms, which is basic component of chemical science, and I force the atom to meet such a way that I form a nanoparticle. I said, okay, I want a 2 nanometer, hundreds of atoms which come together and form a 1 nanometer. So the scientists can dictate these atoms to form different nanoparticles. This is possible. Don't say this is very simple. It's very much possible. And that's called the bottom up. You start with atoms and molecules and force them to be in a proper direction to get you not only the size, but you can also make it different shapes. Whatever the shape you can imagine, you can make nanoparticle of those shapes. And the size and shapes, also their morphology, the surface smoothness, also play the role in any functions. And lots of applications that there. So you have strain resistant clothes, you have external walls which can purify the air, you have a material which can detect the diseases earlier, you can prevent virus infection by coating the surfaces with some sort of nanoparticle. There are lots of applications that you can think about. Quantum dot LED is another good example of this. This is another external example, right? Because in our country, one of the biggest problem is whatever Western world does, we run behind them. We think they are the Western and they are the right one. And our own thing, we have this unfortunate tendency to ignore. But if you really read, there are many deep knowledge in our ancient text that unfortunately we ignore and we should not now. And we should use our modern technologies to go back and see what is in there, why they were good. One of the examples is gold basma. It's one of the ancient Indian medicine, plant medicine, Ayurveda. And they found that the medical benefit of this one of basma is because of the gold nanoparticle in there. They use some TEM analyze. There were lots of papers. This is one of the papers, another major paper, where they showed that there is nanoparticles. And then they were researchers, they tried to study and see how do we play with the nanoparticles to improve the medical benefits of people. And there are lots of these examples. So now I will come back to the main topic and explain to you how we use nanotechnology to combat climate change and develop these nanomaterials. So what I said that we need to absorb the CO2, capture the CO2, bend it, again give the energy. So this is what I will do. So that means I really need a surface which can take lots of CO2 inside. Right? That's the first criteria. Capture lots of CO2. And this is where we design this material. It's a silica, pure silica, having a nano scale size. And it has this dendritic fibrous morphology, that's what we call it the DFNs. It has a particle size from as small as 50 nanometer, as big as 100 nanometer. We can choose the size of the particles. It has a very high surface area. For those who don't appreciate the number, so if you take a 1 gram of powder in your hand, it's like a 1 football ground surface area in your hand. And you can use that surface area to now capture CO2, capture water, capture hydrogen. The first step in the process of conversion. And by the way, this is our invented material. We have many patents, and now this is like one of the few examples where Indian discovered something which is used by the international community. More than 150 groups are now exploring this. And you can see highly monodisperse particle size distribution. They are fibrous in nature. So in our lab, we are fundamental chemists. So we not only cook something, we ask some basic questions. Some of the questions that we ask is here is why my particle is spherical? Why not some flat surface? Why not this shape or other shape? Why the morphology is fibers? Why not a smooth surface, a smooth spherical particle? We ask some of these very fundamental questions. The idea is once you understand the formation mechanism of these materials, you can use that knowledge to design a new material. Right? Because you will see these materials may not be good in all applications. So you need to find a new material which will satisfy your need. So that needs the basic understanding. So how did we make these materials? This is a typical mechanism. It's a bit technical, but I will try to explain. CDAR is a molecule which has this quaternary nitrogen as a head and CH2 as a tail. So it's a polar head and a non-polar head, very simple surfactant molecule. And we all know that when you add these surfactant molecule into some solvent, the water or pipe, they form a micelle. Very basic chemistry, I think you learned it. So this is shown in the cartoon as a blue ball is a quaternary nitrogen, polar head, and the zigzag line as a non-polar head. So I will skip this and show you the animation. So these are the molecules, quaternary head, zigzag line. Added them into a solvent which is a mixture of water and saline. And the concentration of these molecules is such that there will be lots of pollution, lots of problem. So by nature, the system tries to self-assemble to minimize the total energy of the system. So they are self-assembling now, and you can see this system will have a stable stability. But the quaternary nitrogen can repel each other, right? They're all positive charge. So we added one more molecule. This is pentanol. So red ball is OH and zigzag line is CH2. They go in between some of these and stabilize these two interfaces. Idea is to stabilize. Now what we learn is these lamellar phases are not flat in the solvent, but they form some sort of a droplet, some sort of a microemulsion droplet. And these are the droplets which are my template, which are my fault where I synthesize the silica or any phase. So these droplets are made up of a CDAR, water and saline. So these are ideally not a nanoparticle, these are nano droplets. And in the channels, you have a silica precursor, you heat silica precursor to break down, it will give the silica exactly the way these particles may like. Right? And then we also learn the experimental condition where we can keep them away from each other. If they are away, you get a small droplet and you can make as small as 50 nanometer particle. Or you can tune the reaction conditions such that they merge together. By merging, they don't change their internal morphology, right? Because then you don't get a hybrid structure. And then you can make a bigger nanoparticle. And that's how we were able to tune the particle size from as small as 50 nanometers as big as 1200 nanometers. This is generally very challenging in the field of nanoscience where you can get such a huge particle size range. So now, after knowing this, the only challenge with the silica is in insulating material. We know that silica doesn't absorb any light. It will absorb deep UV, but not the visible, not the IR that we want from the solar energy. So now, what do I do with my silica, which has all other nice property like high surface area, Poisson distribution, can take all the silica, but unfortunately, it doesn't absorb the light. So now we need to do something with the silica so that it starts absorbing the light because I need to harness the solar light to give it to silica. So there we use this concept of the goal that I explained to you, the electron cloud which reflects the light, no more reflects the light, but they now undergo resonance. So the idea is now take the silica, coat it with a gold nanoparticle, and those gold nanoparticles will help me to take the photon. Right? The only challenge is if I put a 10 nanometer gold onto the silica surface, it only harvests say around 550 nanometer wavelength visible light. What I really need is every single photon coming from the sunlight. And that's where we came up with the idea of black hole. And I already explained to you, but I will also again explain to you. So you can see here in the cartoon, we tune the distances between the gold particle. And this is again not trivial. How can you tune the distances? You can change the side shape. But this was one of the first examples where we were able to tune the distances by tuning the inflation growth processes. And we showed that when you bring them at a very optimum distance, not very far and not connected, they start absorbing all the light coming from the sunlight. It's like a broadband light absorber starting from 380 nanometers up to 1200 nanometers, all visible and near IR. That's why it's black. And then you put in CO2, it converts into methane. Methane is your CNG. Right? I showed you that concept of carbon economy where you wanted to convert CO2 to methane, burn methane, get the energy, and again CO2 back to the methane. This is exactly happening here. Exactly happening here. Right? So this looks like a great work, but there is a problem. We have good surface area, we have good light harvesting, so-called fancy black gold. But the problem is the rate at which I want to convert CO2 to methane is not that great. It's very poor, right? We publish in big journal because it's more a concept. But idea our group is not just hold at the publication, but one day translate into technology where we need the support from the engineers. But I'm just like also tell you a journey of a fundamental discovery to a commercial process. What are the challenges we face? So one of the challenges here is now I can harvest all the photons, but still the activity is low. Still the activity is low. We don't have the link. Now what could be the reason? If I am harvesting all the photons, it should have been a good catalyst, but it is not. So the reason is, how does it work? This is a bit technical, but I think you guys will be able to explain, understand. So I said metal has this electron cloud onto the surface. Nanoparticle will also have the electron cloud on the surface. So the black gold has a surface which has this electron cloud. It took all the photons coming from the sunlight. Now you can imagine this particle is full of solar energy, full of those photons. So they need to do something to use that energy. So what they do, they give that energy to the electrons. Again, I'm trying to simplify a bit so that everyone follows. So they give that energy to the electrons. The electron goes to the higher energy state, excited state. We call them excited electrons or hot electrons. So they go from the theory. An idea is that take these electrons and give it to CO2, give it to water. They becomes very reactive and reaction happens. So this is the basic idea. Material takes the photons, electron goes to the excited state. I take this electron, give it to CO2. The problem is here. It's easy to explain. Problem is this electron don't want to go to the CO2. It goes back and meet the hole in the material. And this is the biggest problem we are solving from last 50 years now, more than 50 years. All the scientists across the world is the how do I separate these two best friends, hole and electron, from together and force that electron to go to the CO2. It won't go, right? So we came up with the idea in our next. So this was discovered in 2019. Now around 4 years it took for really come up with various ideas and do the system. So idea is this here in this cartoon. So you have a gold, you created the electron, all electrons in the gold. So what we did, in addition to the gold, we put in another nanoparticle, nickel. Nickel metal has empty space, empty orbitals. You can think of some sort of empty space. So when electron goes to the excited state, because the nickel has an empty state, electron goes to the nickel. He is happy, the electron is happy to go to the nickel. Now electron is in nickel, hole is in gold, you separated them already. The best friend is separated. And now you can take that electron and give it to CO2. And the nickel is also good in taking the CO2. Nickel is also good in bending and stretching the CO2. So CO2 is already sitting on the nickel. Now you also have your electron in nickel. And that changed everything. Now the rate of this reaction is maybe 1,000 times more than a normal band. And look at the idea, just simple adding of the nickel. Obviously with all the theoretical understanding. Okay. And obviously I'm only showing you the positive results. There are lots of failure, which we generally don't care, right? But you can see a quick glimpse of how the ideas can help you to improve the catalyst dramatically. And this is something now we are trying to commercialize with the help of innovators. Obviously, there are still more challenges. What is the other challenge here is, can skip this, is the black hole synthesis itself is very challenging. It takes around 1 week to make a few grams of a black hole. And no industry will wait for that long. So now again, this is 2024. It took us 5 years to then convert that complicated process into a one-pot synthesis, and now we can make the black gold in a few hours. Same process, but it took us a long time. It's not that straightforward to convert the complicated synthetic processes into a simpler. Another question that you all can ask is: gold is expensive. We all want that as a jewelry, not as a catalyst which is taking care of the CO2. So it may not be a logical thing to use a gold as a catalyst to take care of CO2. We also thought about that. Simple, so the answer is you use silver, you use a copper. It does work. But the problem is exactly why you guys don't have the copper jewelry, because they oxidize. Whenever they see the air, they oxidize. They are highly reactive. And that's why you get a good catalytic system, nice rate, but it catalyst dies down in few hours or few days. And catalyst by definition is something which should be active for hundreds of hours. I believe this you want something which is for 1 year with the same activity and same selectivity, which you don't get by copper or silver. You get it from the gold. Although we came up with another material, nickel nitride nanosheet, nickel is also cheap. And it does give you the same activity and same selectivity, but we had the same issue with this. It is not stable. These nanosheets break down with time and doesn't give you a gold stability. Now I also want to tell you something about the economics of the process. As soon as we think that, oh, it is expensive gold, the process will be expensive. That may not be true. Because if I'm using a very small amount of gold and converting huge molecules of CO2 to the product that I require, and the rate of the reaction is very fast. So I have a good rate, good selectivity, and the catalyst is extremely stable, say for 1 year. So even if I'm using expensive gold, the overall process will be economic. Because I'm using very small amount and it's very stable. So we should not, when we think about the economics of the reaction, it should be an entire process and not just the catalyst. Several times the amount of catalyst that we use by definition is a very small amount. Right? Okay, so so this is the part where, so my group divided into two parts. One is about this, what I explained to you, develop a material which activates CO2, takes the photon and convert it into products. And this is called photocatalysis. But the problem with the photocatalysis is a big leap. If this is successful at industry level, this is a big change. This will solve our problem, really, seriously. But the problem is, whatever we do in our lab is a few milligram. You take a few milligram of a black gold, put in the light, surely all the particles will see these photons. Industry would not do it in a 2 milligram. They will need tons of black gold. Now you fill reactor with a tons of black gold. Only the surface will get a light. The particle inside will never see that. And then entire process will fail. So here now the next step of this entire process is developing a catalytic reactor. More chemical engineers now. How do I design a reactor where I don't need to feel this way? Can I think about a system like a solar panel? I create a thin layer of black gold and then I pass the CO2 onto it, right? Or I can think of some fluidized bed where I make the black gold in a fluidized bed where every particle is surrounded by CO2 and then put the light. So these are the things that we are also collaborating with different engineers, different companies. And if that helps, if that work out, then these are the catalysts which is already ready. The catalyst is stable, reactive, has the rate that is required for commercialization. So the only challenge in this field is a catalytic reactor design, which many of us are trying to do. But why do we do that? Since we know that we don't have time, we don't have enough time to combat climate change. We cannot, if this entire thing is failed, then this is bad. So we need to come up with something else. We need to have many alternatives. Other one is called thermal catalysis, which is a process which most of the industry uses. Like put something in a metallic tube, put a furnace, you heat, convert. Right? That's something well known. So we also thought of designing a material which doesn't require any light and can be done by a thermal energy. Now, another thing that I wanted to tell you, let us assume that this is the reaction that you want to achieve. And this is what the global CO2 emission is going to be gigaton a year and India is 2.7 gigatons. Let us calculate amount of catalyst required if I want to convert 2.7 gigatons of CO2 to some product, in this case, syngas. We did some calculation. We assumed some catalyst ABC or CDR. We assume this is your rate, productivity. That means around 50,000 millimoles of CO2 converts into CO. That's how you read the rate and the stability in the year. And what we found is it required just 142 tons of catalyst. Which is actually a small number if you think about the industry. It's nothing. Right? So if that is the case, if just 142 tons of CO2 to take care of our climate change, why is it not happening? That's the question. The question and the answer is there's a trick in my calculation. What is the trick? This particular number. This is an unrealistic number. The best number known today in terms of rate is around 5,000. And what I believe is a 10 times more. And if research is extremely challenging. Going from 5,000 to 50,000 may be hundreds of years. Or maybe a 1 day. That's how the scientific discoveries are, especially the fundamental discoveries are. So in one of the group meetings, I said exactly the same to my students, saying that we reach 5,000 and what we want is 50,000. Is it possible? What do we do now with our system? What are the ideas we should come up with that we get such a number? Now I would like to explain to you how we really design a catalyst. How do we think and how do we go with the journey? So the first thing that we did is the catalyst, most of these high temperature catalysts deactivate. The reason is our nanoparticle is good, but if they are so small, they rather than reacting to the CO2, they react with themselves. So 1 nanometer, another 1 nanometer become 2, become 4, 20, 100, and the catalytic activity dies down in a few hours or a few days. And that's what we don't want. We want the catalyst to be stable for years. What could be the solution? One can say, oh, change this metal, that metal, change the size. None of this works. Always reactive because that's by definition analysis. we ask this question: can we not use the metals? There's no metals. There's no issue of sintering and particle size growth. Now, if you don't have the metal, then how do I pull the CO2? How do I break down the hydrogen? So then we came up with the idea of defects. Silica, the sand, is made of silicon oxygen. It's a random silicon oxygen. So we ask this very basic question: can I not take out some of the oxygens from the silica? Can I not create these oxygen vacancies, oxygen defects in the material? Because now you have a surface with oxygen deficiencies. CO2 has oxygen. So when CO2 sees that there is a place where there is no oxygen, the oxygen of that CO2 will quickly click into that oxygen and it will again break down, again stretch the bond. That's what we need, that's activation. And that's what we found. This is one of the very first discovery where we found that you don't need a metal, you don't need any fancy reagent, and simply defects can convert CO2 into methane. That's the first discovery in 2010. However, the rate of the reaction was not that great. It doesn't match with the metal. It's like 90% less, and it cannot be commercially viable. So what do I do now? I still want the same rate and the same stability. So that then we realized that we need to go back to the metal. Then we ask this question that if the problem is the stability of the metal, what do I do using this defect that stabilizes the metal? And this is called some sort of a term, strong metal support interaction, SMSR. What it is you have a plane surface, you put in copper onto it, the copper nanoparticle moves because there is no strong interaction of the surface with the copper, and when they move, they meet together, they grow and they deactivate. We said, okay, let us create the defects, and copper then sits onto the defect. That defect holds the copper, and there is some sort of strong interaction of the metallic copper with your support, and then they don't move. And if they don't move, they cannot meet. If they cannot meet, they will be stable for hours. And this is what exactly we showed here in this paper, where we removed the oxygen from the air, we created oxygen vacancy, we put in the copper, and now copper is extremely stable. Obviously, it's not only stability, we are also able to increase the rate of the reaction slightly. However, even after doing that, the rate was 5,000 millimole per gram, and our dream number is 50,000. Now it's again difficult, right? We tried particle size, we tried defects, we tried everything, and it's still at the bottom. What do I do next? I'm just trying to give you the difficult life of a scientist. If you really put in some sort of a big goal, and now concepts are over, right? Whatever we know in the literature is done, and that's where the students will be thinking. So how do we tune the kinetic behavior of the surface? Let's try to go a little bit technical. So it's about the copper. It's the surface potential of the copper, some sort of energy of the copper surface, which is based on the electronegativity of the copper. Right? That decides how strongly CO2 binds. And in catalysis, it should not bind too strong. If it binds too strongly, it will never heal. You want CO2 to come, react, CO2 go out. Right? That's the process. If you bind too strongly, it won't go out. If it binds too weakly, it will come and go without a reaction. So you need to find that optimum binding strength of the reactant and the product with your surface, which looks like by simply putting the copper is not possible. That means I need to tune the electronegativity of the copper. How do I do that now? I bring in some other metal which has a different electronegativity. Say copper is one metal, I put another metal which has a different higher electronegativity. This metal will pull some electron from the copper, and then overall surface potential will be different, and that will have a different binding strength. This is what exactly we did, where we use two more metals now: copper, nickel, and zinc. These three metals work together, pull electron from each other, and we also use the defect, which has ability to pull, ability to build. I'm not going into the very technical details, but that allows you now in this work. This is very recent work published 2 weeks ago, and this gives you the number which is around 49,200, around 50,000 millimole per gram. The number that we dream. And when I say this, my students laugh at it. They say, it's impossible. But now look, after a few years, we have that number. And by the way, even before publication, even before patenting, I had one of my friends was in BPCL, he's R&D head of the BPCL. I showed him his result. He said, wow, let us upscale. So even publication happened now. We started trying to upscale this at 6 months before with the BPCL, which is one of the biggest industries in our country. Obviously, it's not done. the most of the failure comes from lack to upscale. 99% time they don't upscale. You can upscale, but they don't behave exactly the way we are. Although our calculation is even we achieve 50% of what we achieve at beginner scale, it is still commercially viable. So hopefully in another 6 months or 1 year we know that whether this moves to the next stage, we have to go back to the drawing board and come up with a better case. That's how we do. Right. So I think I've spoken much. So I will skip all of this and I will just spend two minutes of this and I will end. So plastic is another serious challenge that chemist and chemical engineer can solve. This looks dangerous, right? But there is even more dangerous thing than this plastic, which is microplastic. The plastic that you don't see, but it is there in your water bottle, in your food. There are the recent results where they found the plastic in the brain. I don't know how it went. But it's extremely dangerous. Obviously, the simple solution in the weakest societies start behaving, not throwing the plastic. Right? That's all most of our problem. But that is not happening. So can we not convert back the plastic into the basic molecule from where the plastic is made? And this is one of our catalytic systems where we showed that yes, the best plastic can be converted into small molecules, and you use those small molecules to convert back to different products. Obviously, all of the work that I showed you is at the lab scale. None of them we are attempting with different industry, different projects. But these are all at a lab scale, and we learn whenever we fail, we also learn why it's failing. We go back to the lab, design a new material, and again, so it's a cycle that we keep adapting, and one day, at least my dream is to one process goes to the commercial scale that other than only up to the publication. Right, with that, I like to conclude. I showed you the strength of a nanotechnology to design a new material, not only new material, but change the properties of the material by simply changing the size and shape. I also showed you the use of a nanotechnology to harvest sunlight and conserve energy. Use these two concepts to have these carbon cycle and convert CO2 into useful product. And if we achieve this, we will have a green planet and we may be able to combat climate change. With that, I'd like to thank my group. We at the Alpha, by rule, cannot have more than 6 years. That's a rule Baba made that so that you focus on quality rather than running behind the rat race of publishing. So we have a very small but very talented group, and this effect work was done by Charlie Singh. The blackboard work was done by Rishi Verma and Gunjan Sharma. Saidi works on this plastic degradation. Sushma is the lab manager, and Rohit is a student. Most of our funding comes from Department of Atomic Energy, and then we also have funding from Shell, BASF, HPCL, currently BPCL. And you must have seen, although I'm from chemistry department, the work is a mix of chemistry, condensed matter physics, spectroscopy, many things. And no single person can do that, right? It's easy to speak, but not easy to do and analyze the data. So we have a huge amount of collaboration. We use first NMR to see the surfaces, a molecular structure of the surfaces. In collaboration with Amrit, Oliver, we do lots of theory, DFT and all other theories to really understand how these molecules are state bending, how much is the bond angle, how much is the length, how it changes, all of that with many other theoreticians from different institute. We also use spectroscopy and say electron excites from the gold, goes to the nickel. What is the truth? It's easy to say. So we use lots of these spectroscopy to prove that yes, the electron is really going from gold, and that's possible to monitor. And we also do the small X-ray absorption spectroscopy and in-situ transmission electron spectroscopy. I told you that when you have a defect and your particles they don't move. Again, how do you know? So we use this in-situ TEM. I did not show you the video where you can clearly see that when there is no defect, the particles are moving. You can see by your eyes. And when as soon as you create the defect, particles stop moving. A magical video when I went to Germany for 1 week, and when I saw that, wow, I said, wow, my concept is working. And that's the happiness is the biggest part, more than the award that we get. Right. So we have lots of collaboration. With that, I'd like to thank you very much for listening to me, and I'm more than happy to answer the questions. Yes.
Yeah, this is Rajesh Viniwale.
Yes, Rajesh, nice to see you.
Yeah. This is regarding your plasmonic blackboard. I had a curiosity, this is just because I actually have thousands of questions for you, but that I will save for the personal discussion.
More than happy to answer all of them.
But not now.
Yes.
Just, is it it possible that the platinum can play the same role in the plasmonic platinum, because platinum has got all the properties which you are desiring to have, including the electron donation and the kind of, in fact, your additional properties such as if it is along with some support, has got some hydrogen spillover or proton spillover properties. So is it possible or it is reputed?
Ideally, all the metals can be plasmonic. The metal has the plasmonic behavior is based on how mobile the electrons are. And metal electrons are conducting electrons on the surface, so they are all they are ideally all plasmonic. Only caveat is we want a plasmonic which is in a visible range. Platinum, nickel, aluminum, they all use UV light, and UV portion is just 5% coming from the sunlight. So if you are not worried about using the visible light and you are okay with the UV light, then you can use the light, because ideally it has lots of better kinetic behavior than the gold. But the advantage of gold is it takes the visible photon. Although there are now ways where I still use the platinum, put some amount of a thin layer of platinum oxide, change the refractive index, and that allows you to tune the plasmonic behavior in the visible. Not achieved yet, but there is a possibility. And this is one of the directions what I am considering.
And second question, just another fun question. Generally, what you are showing is a reverse of water gas shift reaction.
Yes, it's part of the list.
And water gas shift reactions are quite typically known to produce hydrogen or all other properties of the requirement of hydrogen even for the hybrid wash process.
Yes.
Yes. So now, how do the conflict be resolved? Because there is a process which we need hydrogen, and water gas shift reaction, particularly goes to the steam engine reforming, we definitely take it forward. And then on the other side, we say that it has to be reversed to save the planet.
Yes. So if you want to save the planet, we have to reverse the reaction. If you don't want to, you have to continue doing what we are doing. Exactly, you said the answer. So if you need hydrogen, don't use the water gas reaction. That's what hydrogen emission is. I split the water, I do electrochemistry or photocatalytic or thermal water speed or nuclear nowadays, and get the hydrogen from there, right? If we continue the way we are, we will be more CO2. So we have to, by definition, we have to reverse the thing that we are doing currently. There is no alternative if we want to be resolved.
Thank you.
Yes.
I've been working on life cycle assessment. I was just wondering that is there any assessment that has been done for the catalyst that is being made? Though it is only for lab scale. So is there any investigation that is done?
We did some very LCA, not the real in-depth LCA. We need to collaborate. I think we don't really have a good expert. I think I don't know a good expert who can do the LCA. But LCA is extremely important. Before you really want to do anything with your process, as soon as you think that your process is really scalable and commercially viable, we must do this. We are doing it now for the BPC. But we have some sort of idea when we develop the technology, because the other LCA for some other catalytic system is, say we have other catalytic system which has some reaction rate, similar reaction temperatures, activity, and the LCA says oh, this is not commercially viable. And we know the reason is the rate. Rate was 5,000. Now we have a 50,000. So even I don't do a proper LCA, I know that this is going to work. But obviously we must do it, and if you are expert, more than happy to collaborate. Yes, someone just behind back one.
Good afternoon, sir. Sir, as you say that we are using SiO2 nanoparticles, that is silicon nanoparticles, for capturing that SiO2. Yes, sir. After that, we are introducing gold nanoparticles for increasing the absorption capabilities of light.
Yes.
So that gold nanoparticles can alter the properties of hydrophilicity of SiO2 particles.
Yes.
So how can we overcome this?
Yes, very good thought, very good thought. So because hydrophobicity, surface property also matters in most of the cases. Luckily here, the hydrophobicity is not the real reason for CO2 capture. It's more of a resorption in the empty space between the pores, between the piles. So and code will not really dramatically change the hydrophobicity. In fact, code also help you to resolve lots of CO2. But in the cases where this happens, then you can introduce one more functionality which helps you to maintain the hydrophobicity or hydrophilicity, that we call it the hybrid material functionality. There are ways to tackle these challenges.
One more question, sir. If we ऐसी एक लिमिट हो सकती है क्या साइज लिमिट ऑफ दैट gold nanoparticle? Because I have know about less than 2 nanometer gold nanoparticles can reduce their properties of absorption of that light particles due to quantum confinement.
Yes, very good. It looks like you're learning in science. Very nice. Yes. So if you really go to nano by this is our thinking, right? Nano matlab chota and everything is small, it will be good. Not true. It's always some sort of a range. If you go too small, very particle size, quantum confinement is one reason. Where you split the energy level and their like absorption behavior dramatically change. So you need to have a bigger gold particle. You correctly said more than 5 nanometer. Into that they don't show the property. It also affects the binding strength. If it is too small, they have a huge surface energy, and then when CO2 sits onto them, it never heats, and the catalytic cycle stops there, right? So you need an optimum particle size to decide the light harvesting ability, and you also need optimum particle size to decide the binding strength of your reactant as well as the product.
Thank you, sir. Thank you.
Hello. Very wonderful lecture, sir. Actually, what I am thinking, many people are working on graphene, and many research publications show that graphene can be combined with metal nanoparticle. And what you said that electron capturing and all these things. So why can't we think about this?
Graphene is a zero band gap material.
Yes.
I think it will harvest any photon access. Graphene is good in electron conduction. So
Yes.
I told you that the separation of the electron is a problem. You need to separate, and the electron has to go to CO2. So graphene has this nice electron mobility behavior that once it forms, it moves very fast. So there you can use graphene as some sort of a medium to conduct the electron from your light harvester to the reactor, CO2 in this case. But graphene as a light harvester may not be a waste, but you never know. You can functionalize graphene, break down the band gap, and they may start absorbing. There may be a work, I don't know, I don't work in graphene. There may be already a papers where they made it like that.
Thank you.
Okay, thank you very much, everyone.
Hello. Hello. Yeah. Thank you so much, sir, for your interesting session. Your passion for work was evident from the way in which you were presenting everything. As we move to the last part of the session, I would request Dr. Neeraj Khatri, sir. Before that, I would request Vaidya sir to please felicitate him with a shot. Now I request Dr. Khatri sir to please propose a vote of thanks.
Honorable Vice Chancellor, Dr. Vaidya sir, today's speaker, Professor Polshettiwar sir, many dignitaries in the audience, all deans, directors, head of departments, teachers, and my dear students. It is my great pleasure to be here to propose a vote of thanks. At the outset, I would like to give my heartfelt thanks to Professor Polshettiwar for giving so nice insights to the nanotechnology for sustainable development and energy. The way in which he has presented, the work he has done in last so many years, it is of great national interest, not only of national interest but of international interest. And in the recent years, what breakthrough he has got in his research lab, that is tremendous. That is commendable work he has been doing. And for that, in the last year only, he has been awarded Bhatnagar Award, Shanti Swarup Bhatnagar Award. So I would like to thank very much, and we are also interested in having a collaboration with DIFR and with you, sir. So you will be a guiding force to our students, faculty members, where we can work together for the benefit of this nation. We are the new university, but at the same time we are having energetic faculties and the students, those who can work on the scaling up of the things, particularly the chemical engineering, chemical technology, the chemistry people, material people, those who are working here. So it is very promising area where we are having a lot of scope on doing work on not only on the carbon capture but conversion of that carbon dioxide into the very useful and economical things. Similarly, in short, what brief you are given about the plastic material, that is also giving very much a good insight to our student. So thank you very much from my bottom of my heart. Thank you very much, sir. I would like to thank my Vice Chancellor, Dr. Atul Vaidya sir, for bringing Professor Polshettiwar here to give insight to the students, to encourage my students, to give the latest topic on which the research is going on. And what is more important from Professor Polshettiwar's today's talk is that where there is a gap, where you can work as an engineering professional, where you can have the different types of problems that you can overcome, which are placed over there. So I would like to thank Professor Vaidya sir for giving this opportunity to my students, my faculty member to interact with Professor Polshettiwar. I would like to thank our POG members, Ajay Deshpande ji, the Neelam Gurde ji, all my deans, directors. I would like to especially thank Biniwale ji, Rajesh Biniwale, who came here and has asked a very important, very good questions. So that is also elaborated by Professor Polshettiwar, which is also very encouraging for our students that how people have to think and how you have to see the research which is going on. I would like to thank my colleagues, Vijay Tangre, Dr. Archana Chaudhary, who came here only to attend Professor Polshettiwar's today's talk. I would like to thank my all students from MSc, MTech, then BTech students who are here to listen. Very nice presentation and nice talk by Professor Polshettiwar. I would like to thank Professor Meshram and Professor Saurav Dogrekar for coordinating this program. At the last, I would like to thank everybody who has helped in organizing this program. And once again, a great thank you to Professor Polshettiwar for giving this opportunity to my students and my faculty. Thank you very much.
With this, we come to an end of today's session. Thank you so much, sir. Thank you everyone for attending. Thanks.